Hi, in this chapter we're going to be talking about datums, datum features, and datum references. So here's our objectives. 1, define the difference between a theoretically perfect datum and a datum feature. 2, how to create a datum reference frame through references made in feature control frames. 3, utilize all methods for identifying datum features, including the use of target points, lines, and areas. Number 4, make datum feature references in a feature control frame using the correct order of precedence. 5, explain how datum reference frame may be simulated when 3 mutually perpendicular surfaces are referenced as datum features. 6, use material boundary modifiers on datum feature references and explain the significance of these modifiers. 7, identify the degrees of freedom constrained by each reference datum feature in a datum reference frame. And then we have our terms. Please be aware of the terms. So let's start with some definitions. Tolerance specifications can be used to define relationships between part features. That's what we get into datums about when we start defining the tolerance of relationships between part features. Relationships between part features include position tolerances, orientation tolerances, and profile tolerances. If you recall, the last section we did, we talked about form tolerances. Form tolerances had no datum references. But position tolerances, orientation tolerances, and profile tolerances do have datum references. Okay, let's talk about some more definitions. A datum feature reference. These are the letters that are shown in the feature control frame that establish the datum reference frame. Now, datum features, on the other hand, are the physical features of the actual part. They can be physical, they are physical, and they can be touched. Okay, so a datum feature is the imperfect physical feature on the part. Center lines, center planes, and theoreticals cannot be datums. They cannot be touched. Okay, so datum features are the actual imperfect physical features on a part. Whereas a datum, on the other hand, is a theoretically perfect point, line, or plane. They are located by the physical datum features identified on the drawing. So a datum is theoretically perfect, whereas a datum feature is the actual physical feature on a part, and it's imperfect. And datum feature references, those are the things that we're going to be putting in feature control frames to define the datum reference frame. Okay, so now, datum definitions. Okay, this one here on the left, that is absolutely incorrect. What we tried to do is we tried to put a datum to a center line. A center line cannot be touched. Okay, datums have to be physical, and they have to be touched. Okay, so in this case, what we've done here is we've defined datum A as the diameter of this end of the piece, and datum B as the diameter of the end. These are good datum features because they can be touched. In this particular case, what we're doing here is we're having a total runout tolerance to a datum that's established by A and B. So essentially, by picking up imperfect datum A and imperfect datum B and establishing a center line through those, we've actually done what we call a compound datum here. So the datum extends from A to B, and then these two surfaces here have a runout tolerance with respect to that. Okay, so here's an important concept called a datum simulator. A datum simulator is a theoretically perfect simulator that corresponds to the shape of the datum feature on a part. For example, a plane simulator may be brought into contact with the flat surface of a part to establish the location of a datum plane. Datum simulators provide a surface, axis, or point from which measurements can be made on a part. So I want you to think of datum simulators as something that you use to check your parts, something that are used to simulate the location of a datum. We'll talk more about this, a lot more about this. Okay, datum reference frame. This is another definition. This one's made up of 3 theoretically perfect, mutually perpendicular planes. These planes are located the 3 axes of the part, the X, Y, and Z. Okay, so what we have here is we have 3 planes, mutually perpendicular planes. We have a X axis here, we have a Y axis here, we have a Z axis here. Okay, so we have 3 mutually perpendicular planes. Now, datum precedence. Okay, datum precedence is the order in which the datum references appear in the feature control frame. The one that appears first is always the primary datum. Okay, the one that appears secondly is the secondary datum, and the one that appears third is the tertiary datum. So this is a datum feature reference in a feature control frame. In this case, this is a positional tolerance with a modifier and 3 datums, 3 datum references, a primary, secondary, and tertiary. Okay, and here is how a datum reference frame works with a simulator. Okay, so in this case, this part has 2 holes in it. It's a rectangular prism part, and it has 2 holes in it. Those 2 holes, the location, this is a positional tolerance right here. The location of those holes is with respect to 3 datums, A, B, and C, which makes sense. This is a rectangular prismatic part, so therefore there's 3 datums. In this case, datum A is this lower surface. Okay, and then this datum plane A could be thought of as a simulator for that lower surface. The datums are chosen, the datum precedents are chosen essentially by the shape and orientation of the part. Like in this particular case, datum A happens to be the biggest surface of the part. Okay, that's good. That's good for locating these holes because that locates the biggest surface of the part. The other thing, too, is that these holes penetrate the part perpendicular to datum A. Okay, so I have to hold the part on datum A to see where I'm going to put these holes in. So therefore, in this case, A is a very excellent choice of a datum, primary datum. And then if you look at it this way, B here is the second largest surface, and then C is the third largest surface. So to me that makes sense, primary, secondary, and tertiary for this datum reference frame. Okay, when dimensions are not defined relative to datum features, the parts cannot be checked. Okay, so what we're illustrating here is that you get this part. It's a prismatic part, and it's got 2 holes in it, and you're going to check the position of those 2 holes. Okay, well, what are you going to check it to? Okay, you're going to get your dial calipers or your vernier calipers, and you're going to put it on the edge, and you're going to check to the edge of the hole. Okay, but you know what we're saying here is you can't really see if there's a crook or a valley or some kind of imperfection that's going to ruin your checking of that hole. When you're using a datum to check it, we have this datum simulator over here that picks up the surfaces, the highs and the lows, and so you can accurately check the part. Okay, so without GD&T, this is what you're missing. This is how you go about checking your parts. It's not accurate. It doesn't work very well. So GD&T allows us to completely define what our locations of the holes are and how to define parts that actually work together. Because in some cases, in a lot of cases, these datums are defined as physical features on the part that if this hole doesn't fit with this datum, then the part's not going to work. Okay, So I'm going to bring up degrees of freedom in the next movie.